I had a quick question about our assignment.
Sure.
I don't know if you, just a question. I ran the convergence test and it kind of does this weird oscillation.
Yeah, that's fine.
Is that normal?
Yeah, that's fine. So
Okay.
I did kind of the, I mean, I didn't actually do a convergence test for this one. I just plotted.
Yeah,
But that's totally fine. So sometimes it'll go up and down, but then the most important thing is that it stabilizes.
Okay.
Yeah. Great. That looks really good.
Thank you.
Mhm.
I think I have a question about how much to explore.
Sure. Mhm.
Yeah. All right, number two on two parts.
Yeah.
One is the answer says should be -0.2, 4.23.
Yeah.
But I got it like inverted. Where it's -3 for
Oh.
0.2.
Let me check that. I might have swapped it by accident. Yeah, let me check my answer for that one when I go back.
Oh, and for this one, how do you implement this in the MATLAB code?
We're gonna talk about that today.
Okay.
Yeah. So we basically only got as far as this last week, but then we're gonna know how to actually advance it today.
Okay, great.
Yeah. There shouldn't be any MATLAB that's required. You should be able to do it by hand.
Huh.
And actually, today, we haven't even covered that problem was implicit U word, right?
Yeah.
Okay. Yeah. So we're gonna do implicit U word today.
Yeah, I'm just following the lecture notes online.
Gotcha.
Trying to get this one done early.
That's fair.
Friday.
Yeah. No, for sure. It's a busy time. Yeah.
Going at the setup, I'm not actually running.
Yeah. I might cut the number of open form activities down by one just because I know it's gonna be we have no more homeworks after homework 5. I do want to get you guys onto the cluster, but we'll see. I'll see how powerful your guys' computers. Maybe you can do the final project without the cluster. But it would be cool to use the cluster. I think that's a really cool thing for this class. But we'll see.
I did a 50 by 50.
Yeah.
It took me like a minute and a half.
Okay.
I don't know what that's like.
That's not bad. That's pretty good. I think activity 3 is going to be much more expensive. I've been working on it. It's yeah. That one we're going to use we're going to 3D simulations for the first time, and we're going to do a snappy hex mesh, which is like flow over like an object basically.
Oh.
So those are much more expensive. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. All right, so today we're continuing our lecture notes on time marching schemes, and so this is the topic for homework 5. So I think I mentioned last week that homework 5 will be the last written homework that we do, because homework 5 is basically in preparation for the midterm exam. So remember, midterm exam is going to be next Wednesday, so a week from the 15th, which would be the 22nd. So April 22nd in class will be the second midterm. In terms of content, I did post a study guide actually right before I came to class today. And so if you look on the weekly page for week 13, at the bottom of the page there, you will see the study guide for midterm 2. Okay. And basically in terms of content, there's actually not that much content on this exam because we've started doing the open foam stuff recently. It's basically just going to be the contents of homework 4 and homework 5. So the simple algorithm stuff, and then this week on the time marching stuff. Okay.
So open phones.
No open phone. Yeah. Yeah. So hopefully not too much to study. You'll see the study guide itself is actually quite short. I think in terms of content, there's maybe only like 3 weeks worth of content. That's going to be on the exam. So hopefully this exam will not be too bad to study for. I do need to post solutions for homework 4. So I will do that probably in a day or probably tomorrow. So definitely look forward to homework 4 solution, and then homework 5 solutions I will post immediately after it's due, just so you have that for the exam as well, right? So only 2 homeworks, 3 weeks worth of content on exam 2, but we have to do it. Okay. All right, and so besides that, I think. Oh, one more announcement. So the university wants me to let you know that SOQs are now open for this class, which is crazy to me. We're not even close to being done, but I guess you can write your 1-star review with me at this time if you want. It's crazy. I think they've done this for the past couple of years. Like you can write the review starting. You can your SOQs in week 13 or something. It's like are you sitting in a movie theater typing up your movie review? Snape hasn't even killed Dumbledore yet. How can you write a review on the movie so far? But it's there for you. So if you want to vent or anything, you can write your SOQ for the class right now. Okay, and all your other classes technically. Yes. Okay. All right. So that's it for the announcements. Any questions I can answer before we get started for today? Okay. All right. So let's pick up where we left off. Okay. So what we were discussing last Wednesday was time marching schemes for unsteady problems. Okay. So essentially, our last kind of theoretical conceptual topic that we're covering in this class is how do we deal with situations with a time derivative, right? Because our general Navier-Stokes equation, our general conservation equation, they all have an unsteady term, which reflects the fact that, whenever we're looking at fluid flow, they can change with time. Because everything that we've covered up to this point, even the Navier-Stokes, right? We've kind of just ignored the time derivative. We just assume that our flow has been steady, right? Now, there is a lot of interesting scenarios that you can look at in terms of steady flow. All of our open foam activities so far have been steady. But once you start to get to some really interesting situations, those are going to be unsteady. Okay. And what we found was that the time derivative is unlike any derivative that we've seen so far. Because space, for space derivatives, we can just apply just a very straightforward, finite difference scheme to it, finite volume scheme. But time we have to treat a little bit differently because time only really goes just one direction. So we have to go forward in time, right? And so just to kind of refresh your memory, let me go ahead and write out our general conservation equation. All right, so this is just going to be in 1D. And so, we're going to focus a lot on 1D problems. Okay. So this right here is our 1D general conservation equation. And of course, the key point here, or kind of the key addition, is that unsteady term right there. Okay. Okay. And so what we found is that the way that we have to deal with this is through time marching, right? And so we've only really covered this one technique for this, which is the explicit Euler technique. So for this class, just because we don't have that much time, we're only going over two techniques, just explicit Euler and implicit Euler. You'll see implicit Euler later today. I'm not going to go through the derivation again, but we end up with the following expression. Okay. So remember, all time marching schemes are the same in that on the left-hand side of the equal sign, we're going to have everything at the next time step. So everything at n plus 1, right? So for explicit Euler, we get an explicit expression for the solution value at the next time step, right? So that looks like this. So you have Bi n plus 1 is equal to U delta t divided by 2 delta x plus k delta t divided by delta x squared. This is Bi minus 1 n plus 1 minus 2k delta t divided by delta x squared, Bi at n plus minus u delta t over 2 delta x plus k delta t over delta x squared, Bi plus 1 at n. And then we have our source term as well. So q at xi delta t. Okay. So the nice thing about explicit Euler is that we get this kind of very nice explicit expression. It looks scary, but you'll see very quickly that it's the same four variables that's repeated in different combinations. So basically, you're just going to plug in the value of the convection velocity, the value of the diffusion constant, the time step size, and the grid size, and you're going to have coefficients in front of all of these terms. Okay. All right, and so that'll get you kind of one nice expression that you could advance forward in time. So I think last thing that we did last Wednesday before we left was that we started to do an example, and we plugged into this expression, but then we were just about to get started with actually using it to march this forward. Okay. All right, so that's where we're going to start. But any questions on this so far? Okay, this is just kind of a recap from last time. Okay. All right. So let's get back into the example and let's complete it so you can kind of see it from front to back. Okay. Okay. So for this example here, we just have a very simple unsteady diffusion. So we have actually no convection in this problem. We have partial phi partial t is equal to 3 partial squared phi partial x squared with the following boundary conditions. And so we have phi at x is equal to 0 at all times t is equal to 1. And 2, we have a Neumann boundary condition on the other side of the domain, partial phi partial x at x is equal to 1, and for all times t is equal to 2. Okay. And so what we want to do in this problem is we want to use explicit Euler to advance this forward in time. Okay. Now there's only so much we can do with hand calculations. in reality, explicit Euler is something that you would program in a computer and let the computer advance it forward, 100, 1,000, 1 million times, and it can do that very quickly. But by hand, we can only really advance this, 1, 2, 3 steps, before it starts to get very tedious. Okay. So we're going to use explicit Euler. Okay, so we're going to basically solve for the first three solutions. Okay. Okay. Oh, one last thing. I forgot. I always forget this, but we also need our initial condition. Okay. So I think we mentioned initial condition last time, but remember, the explicit Euler is always, you're always making predictions on the next step based on your current step. So you need to have somewhere to start, basically. So whenever you're plugging into this expression up here, you need stuff to plug in for phi n, at least on the first time step. And so that's what our initial condition is for. Okay. So for our cases here, we usually don't have a reason other than to use a 0 initial condition. That's kind of the standard for most CFD simulations anyway as well. There are situations where you want to initialize at something other than 0, but most of the time 0 is the best and the easiest. Okay, so our initial condition in this case is that phi at all values of x at time is equal to 0 is equal to 0. Okay. Okay. Oh, we need the grid spacing and the time step size as well. So let's assume. And by the way, when you do these problems, the time step size and the grid spacing will be given to you. So this is not something that you have to make up yourself. Okay? So let's assume a time step size of 0.1 seconds and a grid spacing delta x of 0.25. Okay. All right, so first thing we're going to do, since we're using explicit Euler, is we're just going to simply plug in all of the parameters into our explicit Euler equation up here. Right, so this is pretty straightforward. The only thing you have to do is you have to make note of the time step size. You have to make use of the grid spacing, and you also have to make note of the parameters from the problem. So the convection velocity and the diffusion constant as well. Okay, so for this problem, but I suppose this is also given to you. This is not something that you make up, right? So you also need values for the convection velocity and the diffusion constant, okay? So for this particular problem, we have no convection because we have no first order derivative with respect to x. And so u here is 0 for this problem, okay? So remember, this is our problem here. Right, so there's no convection term. So if there's no convection, that means convection velocity is 0. And then our diffusion constant k is going to be 3, because that's the coefficient in front of the second order space derivative. Okay. Okay, so let's go ahead and plug all these into our explicit Euler equation. So to do all that, we get Bi at n plus 1 is equal to 4.8 Bi minus 1 at n minus 8.6 Bi at n plus 4.8 Bi plus 1 at n. Okay. All right, so very straightforward. So explicit Euler is just you kind of just start with plug and chug. You get a recurrent. We call this a recurrence relation. So it's something that's going to reoccur kind of over and over. Okay. So now that we have this expression, let's evaluate it at all of the grid points. So for all values of I. So from this problem, we can see that we have a grid spacing of 0.25. From the boundary conditions, we see that the length of our domain is 1, because our boundary conditions go between 0 and 1. That means the number of grid points that we have is going to be 5, right? So our domain looks something like this, right? Where the space in between each grid point is 0.25, and the entire length of the domain is 1, okay? All right, so we have 5. We're gonna have 5 equations then, one for each grid point, just like we used to do with finite differences. Okay, so we have I is equal to 1, I is equal to 2, I is equal to 3, I is equal to 4, I is equal to 5. All right, and then just like we did before, we're going to take our equation here and then just plug in the appropriate values of I for each equation, okay? Some of these equations we're going to replace with boundary conditions, just like we used to do. But the nature of the boundary condition, or the way that we apply them, is going to be slightly different just because we're time limited, okay? But let's just plug in first, and then we'll kind of see where we go from there. Okay, so for I is equal to 1 first. We have phi1 at n plus 1 is equal to 4.8, phi0 minus 8.6, phi1 at n plus 4.8, phi2 at n. Okay. Same thing for I is equal to 2. So I is equal to 2, we have phi2, n plus 1 is equal to 4.8, phi1 at n minus 8.6, phi2 at n plus 4.8, phi3 at n. Okay. And then so on and so forth. I'm just going to write the rest just because it gets repetitive, but you know, you guys can follow the pattern. Okay. So a little bit repetitive, but you know, it's nothing that we haven't kind of dealt with. Okay. Okay. All right, good. So we have 5 equations for 5 nodes, right? So that whole principle that we've kind of looked at in the past, you know, you should have an equal number of algebraic equations to the number of grid points or cells in your domain. Okay. Now for this time marching stuff, you know, we are going back to finite differences just because it is a little bit easier to talk about. But just know that this technique works for finite volumes as well. It's just, you know, we just don't really have time to kind of go through that. Okay. Okay. But before we start advancing this forward in time, there are a couple issues here that we have to deal with. Okay. So first issue is we need to incorporate our boundary conditions, because if we look at the first equation in this system and the last equation in this system, okay, both of these equations here have a value for phi that we cannot access because they don't exist, right? So for the first equation, that is phi0, right? So phi0 doesn't exist because the leftmost node in our domain is phi1. And then for the last equation, we have phi6, which again does not exist for this domain because our domain ends at I is equal to 5. Okay. And so just like we did before, that means that we have to replace these equations with boundary conditions. Okay. Okay. So the way we apply boundary conditions here is going to be very similar, but not exactly the same, right? Okay, so our first boundary condition, let's do on the left-hand side first, says that phi at x is equal to 0 and t is equal to 1. Okay, so that right there is a Dirichlet boundary condition. Okay, so let's go ahead and cross this out just because we can't use this equation here. Okay. So instead, we're going to have an equation for phi I or phi 1 at n plus 1. Okay. So that boundary condition is telling us is that for all values of t, that means, for all values of time, the value of our solution phi at that grid point is going to be equal to 1. Okay. So this equation here is actually very simple. So this is phi 1 at n plus 1. So the value of phi 1 at the next time step is going to be the same value of phi at the current time step, which is just 1. Right? So phi 1 n plus 1 is equal to 1. Very simple. Okay, next let's apply our Neumann boundary condition. So our Neumann boundary condition is on the other side of the domain. So this can be applied at I is equal to 5. And this tells us that the solution derivative at x is equal to 1 at all times t is equal to 2. Okay, so that means we're going to replace this equation here, okay, with phi, our partial phi partial x is equal to 2. Okay. Okay, but of course, we can't just apply a derivative just like that. We do need to, apply finite differences here. So let's do a finite difference approximation for this guy here. Okay. So essentially, we're going to be performing a forward difference scheme here because we need to involve phi is equal to, or I is equal to 5. Or I guess that completes backward difference. And then the neighboring node is 1. Okay. So we apply finite difference here. We have phi 5 minus phi 4 divided by delta x is equal to 2. Okay. And so we can solve this equation for phi 5, right? And so we have phi 5 is equal to 2 delta x plus phi 4. Okay. Which is a little bit of a strange way to write that equation. We've never done that before. But if you look at every other equation here in our explicit Euler system here, we have one value of phi on the left-hand side that matches the value of I, right? So you have an equation for I is equal to 1, 2, 3, 4, 5, and then everything else is on the right-hand side, okay? So we're going to write this equation in that same style. So we're going to have phi 5 on the left-hand side by itself. Okay? And then we also need to assign a time index for both of these, okay? So for phi 5, since it's by itself on the left-hand side, we're going to assign it to time step n plus 1, okay? Just so that we can solve for it. And then for phi 4, since we moved it to the right-hand side, we're going to assign it a time step n, which is the current time step. All right, and so those two equations together will give us the two equations that will fix our first and last ones, and we now have our system that we can start fixing forward. All right, any questions on this? Okay, good. All right, so at this point, we can say that we've applied explicit Euler because we have our 5 equations. Now we can start, actually utilizing this. Okay. And so again, there's not too much we can do here because, unless you want to, you can just kind of repeat the same equation over and over. You can write code for it, and so if you're MATLAB savvy, you can program this fairly easily. It's not that difficult to write. Although that's not a requirement for this class, you don't need to write the math. go for it. Okay. But let's start advancing this forward in time. Okay. Now to start, we have to make note of our initial conditions. Okay. And so for this problem, and honestly, most problems that we're going to do at t is equal to 0, which also means this is going to be at n is equal to 0 as well, right? Because that's the first time step. All values of phi are going to be 0. Okay. That means our first solution is going to look like this. So phi1 at time step 0. Right. Let me do this just to highlight the time step. So in the superscript, it's going to be just like that. Okay. So phi1 at 0, phi2 at 0, phi3 at 0, phi4 at 0, phi5 at 0. Okay. So be careful with the notation here. It does get a bit confusing, but just remember that in the subscript, the subscript is the space index. So that's kind of where that point physically is in space. The superscript is the time index. So that's where a solution is on the time. Okay. But for the initial conditions, very straightforward. It's 0 everywhere. So for our initial condition is 0 everywhere, that means that means we're just gonna have 0 for every solution. Okay. Okay. But right, so even though we set the initial condition to be 0 everywhere, our boundary conditions also have to be satisfied at the initial condition as well. Okay, so it's not going to. So typically, all of your interior nodes are going to be 0, but your boundary conditions may not be 0, but they have to be satisfied as well. Okay, and of course, boundary conditions are only going to affect the value for phi1 and phi5. Okay, so let's go back and refer to our boundary condition equations and see what we should plug in for these here. Okay, so let's start with phi1. So let's scroll all the way back up here for our equations here. And you can see from phi1 that at all values of time, phi1 is going to equal to 1. Okay. So that means that phi1 at time step 0 is going to be 1. Okay, so meanwhile, for time step 0 at phi5, right? So phi5 at 0 is going to be equal to 2 times delta x, right? So delta x in this case is 0.25. That was given to us in the problem. And so 2 times 0.25 is 0.5. Okay. Plus phi4 at n, the current time step. So this is 0, right? So that means phi5 at n plus 1 at the initial time step is just going to be equal to 2 times 0.25, which is 0.5. Okay. Okay. So that right there is our solution on the first time step. I know it's the initial time step, but we count this one as kind of the first one. Okay, so our first time step solution is simply just 1, 0, 0, 0, 0.
Sir,
Yes.
how did you get? What is that fee for? And
So phi4, this is stuck at the initial condition, which is just 0. So phi5 here at n plus 1 is 2 times delta x. Delta x is 0.25. So 2 times 0.25 is 0.5. And then for phi4, we plug in 0, which was the value for
is Is that just because the definition just?
Exactly, yeah. Mhm. All right, any other questions on this time step result here? Okay, all right, so let's do the next time step. All right, so we need to do 3 of these. That's what the problem is telling us. Okay, so for the next time step and beyond is it's kind of the same operation. So we're basically going to write out our full equations from before. It's just that we're going to plug in our values for the solution from the previous time step. Okay. Okay, so for the next time step and beyond, we're just going to use our explicit Euler equations. Okay. Okay, so that means we're going to have equations for phi1 at time step 1, phi2 at time step 1, phi3 at time step 1, phi4 at time step 1, and phi5 at time step 1. Okay. Okay, so let's start with phi1. So that's the easiest one. So phi1 at time step 1 and at all times is just going to be 1. Okay, so phi1 actually very, very straightforward. Okay. All right, phi2. So phi2 is going to be 4.8. Phi 1 at time step 0 minus 8.6. Phi2 at time step 0 plus 4.8. Phi3 at time step 0. Okay. All right, and then for phi3, we have 4.8. Phi2 at time step 0 minus 8.6. Phi3 at time step 0 plus 4.8. Phi4 at time step 0. Okay. And then same thing for phi4 here. So phi4 at time step 1 is 4.8. Phi3 at time step 0 minus 8.6. Phi3 at time step 0 plus 4.8. Phi5 at time step 0. And then phi5, same thing. So same thing as before. So 0.5 plus phi4 at time step 0. Okay. Okay, good. And so all we have to do here is just plug in the values of phi from the previous time step, right? So everything that we have here, so phi1 at time step 0, phi2 time step 0, phi3, phi2, phi3, phi4, 3. Oh, that's a typo there. That should be phi4. I'm sorry. So this should be phi4. Okay. And then phi5 right here, and then phi4 right here. Okay. We're just going to plug in their values that we got from the previous time step. Okay. So everything that we got here, we're going to plug in down here, right? So for instance, phi1 at time step 0, we know that this is 1. Phi2 at time step 0, this was 0. Phi3 at time step 0 is 0. Okay. 0, 0, 0. Phi3, 0. Phi4, 0. Phi5, this was 0.5. Okay. This was also 0 here. Okay, so we plug all those in, we work through the arithmetic, we get, okay. For phi1 is always going to be 1 because of the boundary condition. Phi2 at time step 1 is going to be 4.8. Phi3 at time step 1, 0, because everything is 0 in there. Phi4 at time step 1 is going to be half of 4.8, which is 2.4. And then lastly, phi5 is 0. So this right here is our result at the second time step. Cool. Any questions on how we got that there? So from here, it gets repetitive. So, for the next time step, we're going to apply the exact same equation. The only thing that gets updated is just the values for the solution at the previous time. Okay, so I'm not going to write out the equations again. You can kind of guess what's happening. But I'll do one more advancement just so that you can see. So for the next time step and the last one for this problem. Okay. So we have the same explicit Euler equations. But the values for phi are going to be updated. Okay. Okay, so we go ahead and plug those in. I actually don't even have those in my notes this time for this. But we go ahead and plug those in. Phi1 at time step 2. This is still going to be 1. Okay. Phi2 at time step 2. Okay. This is going to be 4.8 times 1 minus 8.6 times 4.8 plus 4.8 times 0, which is phi3, right? So phi3 is the last phi value that's still 0 from the initial conditions. Okay. So we punch those into the calculator, which I will do right now. Calculator app, open. 4.8 minus 8.6 times 4.8. This is minus 36.48. Okay. Phi3 at time step 2 is equal to, let's see, we have 4.8 times 4.8 minus 8.6 times 0 plus 4.8 times 2.4 is equal to, so 4.8 times 4.8 plus 4.8 times 2.4, that's 34.56. Okay. And then phi4 at time step 2, let's see, so this is going to be 4.8 times phi3, which is 0, minus 8.6 times 2.4 plus 4.8 times phi5, which is 0.5. Okay. This is minus 8.6 times 2.4 plus 4.8 times 0.5 minus 18.2. Okay. And finally, phi5 at time step 2 is equal to 0.5 plus phi4 from the previous time step, which is 2.4. We add those two together, we get 2.9. Okay. Okay. And then from there, it just kind of gets just repetitive. So it looks like the solutions are kind of going crazy right now. So we have, positive, negative, positive, negative. That's because we're only time stepping this, 3 times. If you continue to time step this, then the solution will start to stabilize. All right, but that's the basics of explicit Euler. So it's basically just, you basically just obtain your explicit Euler equation. You just plug in the values from the problem. You modify them according to the boundary conditions, and then you just start stepping forward in time. Okay, and the stepping forward it is a bit tedious. You kind of just have to keep plugging in, but hopefully fairly straightforward. Okay. All right. Any questions on this? Okay, good. All right, so for the second half of class today, let's start talking about implicit Euler, how we get that equation, and then let's start the next example for that. Okay, so next we have the implicit Euler method. Okay, so implicit Euler is very similar to explicit Euler. I mean, they're both named after, they're both credited to the same mathematician, Euler, okay? But what you're going to see for implicit Euler and for implicit methods in general, you do not get an explicit expression for the value of the solution at the next time step. All right, so what we're going to get instead from the from the implicit Euler and just implicit methods in general is that the solution at the next time step is implicitly implied by some kind of complicated expression that we have. Okay, maybe implied is not the right word. It's implicitly defined based on the equation that we're going to derive. And so what that basically means, from a practical perspective, is that implicit methods, they require usually some kind of matrix inversion, but they usually require some kind of solution to a set of linear equations. Okay. Now, if you look at our previous example was nice because we got explicit expressions where it said phi1 at the next time step is this, no ambiguity. Phi2 at the next time step is this. Okay. But for implicit expressions, it's not going to be as straightforward. Okay. So of course, that limits what we can do by hand. So if you come across an implicit problem, you either have to solve it using MATLAB. It's not a complicated MATLAB code. You just have to basically just define a matrix and a vector and just invert them. Or you just kind of have to just set it up by hand. But it is important to know because it is an important distinction because a lot of times when you're using CFD code or commercial code or research code, you usually have a decision whether you can use an explicit time marching scheme or an implicit time marching scheme. And there's pros and cons to both. And so there's no one way that's better than the others. It's a decision that you have to kind of make based on the parameters of the problem. Okay. But let's go through the derivation first, and then we'll talk about when you should use one versus the other. Okay. Okay, so same as before, we're going to start with our general conservation equation in 1D. So you have partial phi, partial t, plus u, partial phi, partial x, is equal to k, partial squared phi, partial x squared, plus q of x. All right, and then just like we did for explicit Euler, we're going to replace all the derivatives here with their finite difference approximation. Okay, taking note of which derivatives are time derivatives and which derivatives are space derivatives, and then just adjusting accordingly. Okay, so for the time derivative, let's go ahead and do that one first. So we have phi I n plus 1 minus phi I at n divided by delta t. Okay. Remember, for the time derivative, we are limited to just forward difference, just because we can't really go too far back in time, so we can't use it can use a central difference here. So that's all we end up with. Okay. Next, we have the convection derivative. So the convection derivative, we have u, and we're just going to use very simple central difference. So you have u divided by 2 delta x, ui plus, or phi I plus 1, excuse me. I was thinking about Navier-Stokes. Phi I plus 1 minus phi I minus 1, okay, is equal to. Next, we have the diffusion derivative. So that's k divided by delta x squared, phi I plus 1 minus 2 phi I plus phi I minus 1, okay, plus q of x I. Okay, so nothing too strange yet, right? So it's just so far we just applied just very basic finite difference to every term, just like we've always done. Only difference, of course, is the time derivative that's there. Okay. All right. So if you notice, compared to our explicit Euler derivation, there's one detail that I've left out of the expression so far, which is all of the space derivative terms. I haven't assigned a time index for them just yet. Okay. So for the convection term, we have phi I plus 1 minus phi I minus 1, but I haven't told you whether this is going to be n plus 1 or n, right? So for explicit Euler, right, for all of the space derivative terms, we assign a time index of n, right? And that allowed us to basically solve. We just had one term in our entire expression that had n plus 1, and we just solved for it, right? For implicit Euler, we're going to do the opposite. So for implicit Euler, everywhere we have a space derivative, we're going to assign a time index of n plus 1 instead. Okay. So for the convection derivative, we have phi I plus 1, n plus 1, phi I minus 1, n plus 1. Okay. For the diffusion derivative, we have phi I plus 1, n plus 1, phi n plus 1, phi minus 1, n plus 1. Okay. So for basically every other phi term there, we have n plus 1. And we now have the opposite situation where we have, every phi term here has an n plus 1. And then the only phi terms without, an n plus 1, which is n, okay, which comes from the time derivative. Okay. We're going to do the same thing we did before. So everything with n plus 1, we're going to move to the left-hand side. Everything with an n, we're going to move to the right-hand side. And so we're going to end up with kind of the opposite situation we had before, where our left-hand side here is going to be much heavier, and our right-hand side is going to have very few terms associated with it. Okay. I'm going to do one more step here, just kind of combine things, just make it kind of space efficient. I'm going to multiply everything by delta t. Just to kind of clear the denominator for that. Okay, so this is a lot of algebra, and so I'll kind of leave a lot of the details to you, but we'll kind of end up with the following result. So we're gonna basically do as we have here, but also group together like terms. So we have just coefficients for phi I plus 1, phi I minus 1, and phi I. Okay. All right, so we do that, we get the following. Okay, so on the left-hand side, first we have the coefficient for phi I minus 1 n plus 1. This is minus u delta t divided by 2 delta x plus, minus k delta t divided by delta x squared, phi minus 1 and plus 1, okay, plus 1 plus 2 delta t times k divided by delta x squared, phi n plus 1, plus u delta t divided by 2 delta x minus k delta t divided by delta x squared times phi I plus 1 n plus 1. Okay. So that's now our entire left-hand side of the equation. Okay. So everything with n plus 1, we've moved over to that left-hand side. And on the right-hand side, we only just have a couple terms. So on the right-hand side, we have phi I at n, right? So that came from the time derivative term, plus q at xi multiplied by delta t. So this right here is our implicit Euler time marching equation. Okay. All right. Any questions on how we got this result from the derivation? Okay, good. All right. So let's talk about the features of this expression here before we jump into an example. And let's also discuss why we would want to use this over the explicit Euler. Because there's really no hiding it here. This is a little bit more cumbersome to use just because we don't have an explicit expression for bi plus 1. Bi n plus 1, excuse me. Okay. So now that we have more n plus 1 terms here, we can't explicitly solve for a particular value for phi I n plus 1. Okay. Okay. So one way you can look at this is that this equation here has technically three unknowns, right? So you have phi I minus 1 at n plus 1, phi I at n plus 1, and phi I plus 1 n plus 1. Okay. Right. So with multiple unknowns in the equation, we can't solve it straight up for just one unknown variable. Okay. So you might be thinking, how do we even solve this equation then if we have three unknowns in only one equation? Well, right, just like we did for explicit Euler, you're going to apply this equation at every single node in your grid. Right, so I is equal to 1, 2, 3, 4, 5. Okay, if you have five grid points, just like our last example. Okay. All right, and so by doing so, and just like the previous examples, you're going to have boundary conditions as well. You're going to end up with enough equations to solve for the unknowns. Right, so trust me when I say you'll have enough, and you'll see in the example that we're going to do after this as well. Okay. Okay, but the only issue here is that those equations, you're going to have a matrix set of equations on the left-hand side of your expression here. Okay. Okay, and so after you apply this at every node in your grid, right, and you apply your boundary conditions, you're going to get a system that looks like the following. So you're going to get basically a matrix here, okay, where that matrix there is going to have all the coefficients from your implicit Euler. It's also going to have the coefficient from your boundary conditions as well. Okay. You're going to have that multiplied by a vector here, where this vector has all of the unknown phi values at the next time step. So this is, let's say phi1, n plus 1, phi2, n plus 1, phi3, n plus 1, dot, dot, dot. Okay. Phi I, n plus 1. Okay. So that goes up to just the number of nodes in your grid. Okay. This is equal to the right-hand side, where everything on the right-hand side is known, right? Okay, so on this right-hand side, we have phi n plus q at xi delta t. Okay. Right. So remember, the reason we have that on the right-hand side is that everything here is known. Right. We don't worry about the right-hand side. The right-hand side, we're going to get something that's known, right? But in order to solve for the vector on the left-hand side, we do have to invert the coefficient matrix. Okay? Which, for most practical purposes, you need either a calculator or MATLAB to do. Okay, so on the homework, I do have you actually doing an implicit Euler by hand, right? So I'm gonna have you advance it 3 steps forward in time and get solution just because you have MATLAB available. But for the exam, you're obviously not gonna have MATLAB available. I'm not gonna expect you to solve a matrix set of equations. And so if you do get an equation or if you do get a question on the exam that asks you to do implicit Euler, I would just ask you just to set up the coefficient matrix and that's it. Okay. Okay, any questions on this before we start working on an example here? Okay, all right, so timing a little bit unfortunate, but just like last Wednesday, we will start an example today and then just finish it up on Wednesday. Okay, so for this example, just like our previous one, we're going to work on an unsteady diffusion. Actually, our equation is exactly the same. Actually, we might finish this just because we can't actually advance this forward in time. We'll advance it once at a time. Okay. So we'll finish up this example and then we'll talk about 2D and time-dependent boundary conditions next. Okay. So so unsteady diffusion with implicit Euler. Okay. All right. So partial phi partial t is equal to 3 partial squared phi partial x squared. Okay. So just like the previous example, we don't have any convection. And so we just have diffusion here. Okay. So U is this going to be equal 0. We have our boundary conditions, same as before. So you have phi at x equal to 0, all times t is equal to 1, 2, partial phi partial x at x is equal to 1 at all times t is equal to 2. Okay. Our initial condition is phi at x, t is equal to 0, is equal to 0. Okay. All right, so just like before, we're going to assume the same time step size, the same grid spacing. All right, and so we're going to advance this forward in time. Okay. Okay. All right, so this problem doesn't need any introduction again, so it's the same problem we did before. The only thing that's changing here is the time marching technique. We're doing implicit U words. Okay. Okay, but our method here is not going to change. So we're basically going to take the exact same parameters from the problem. Okay. We're going to plug it into our implicit Euler equation here. Okay. And be warned, so even though explicit Euler, implicit Euler, they do come from the same equation, but because these terms are on opposite side of the equal sign from before, the coefficients are not going to be the same. Okay. I don't think you'll have a situation. I don't think I'm going to assign you a problem where I have you do both explicit and implicit Euler for the same problem. But just know that, because the positions are different, the signs are going to be different for these terms as well. Okay, so you can't just copy the explicit Euler coefficients, it's the implicit ones. They are going to be different. Okay. Okay. And so we do that, we get the following. So we get minus 4.8 bi minus 1 n plus 1 plus 10.6 phi n plus 1 minus 4.8 bi plus 1 n plus 1 is equal to bi at n. Okay. And there's no source term here, so there's no q term here at all. All right, so applying our parameters here, time step size, grid spacing, convection velocity, diffusion constant, we get coefficients of minus 4.8, 10.6, minus 4.8. Okay, and then just like we did before, we're going to apply this at every single node in our grid. Okay, so we're going to apply this at I is equal to 1, 2, 3, 4, 5. Except, we do have knowledge from the previous problem that we are going to modify this for our boundary conditions. So we're going to apply this at every single node except the boundary nodes. Okay. All right, but let's go ahead and set it up so we can do that. So we're going to have our equation for I is equal to 1, I is equal to 2, I is equal to 3, I is equal to 4, and I is equal to 5. Okay. Okay, so let's do the interior nodes first, just because we have the equation just right there. So it's just plugging in the values for I. Okay, so what I is equal to 2, we have minus 4.8. I minus 1 here is phi1 at n plus 1 plus 10.6 phi2 at n plus 1 minus 4.8 phi3 at n plus 1 is equal to phi2 at time step n, the current time step. Okay. Same thing for I is equal to 3, except every space index is advanced by 1. So we have minus 4.8 phi2 n plus 1 plus 10.6 p3 n plus 1 minus 4.8. What's up?
No,
Oh, I thought I heard professor. p3 at n, and then I is equal to 4, same thing. So minus 4.8 p3 n plus 1 plus 10.6 p4 n plus 1 minus 4.8 b5 n plus 1 is equal to b4 at n. Okay. Okay, good. All right, so now let's implement our boundary condition terms here. So for phi1, for I is equal to 1, that's where we have our Dirichlet boundary condition. Okay. That's not going to change. That's very simple to implement, right? And so our boundary condition equation here is simply phi or phi1 at n plus 1, right? It is a constant Dirichlet boundary condition. And so phi1 at n plus 1 is simply just going to be 1, right? So in some sense, that equation actually is exactly the same as before. Okay, now for the Neumann boundary condition. For the Neumann boundary condition, I is equal to 5, right? Remember, we have the boundary condition phi or partial x is equal to 2, right? And so we do our finite difference scheme here. We have phi 5 minus phi 4 all divided by delta x is equal to 2. Okay. Right, so not so different from before. Okay. All right. But with implicit Euler, we don't have the same restriction as before. So with implicit Euler, we can have multiple phi terms here with n plus 1, just because everyone's kind of doing it. And so we don't really have we don't have to kind of do the awkward thing with explicit Euler where we just assign 1 at n plus 1, 1 at n. We can just assign both of these at n plus 1, just because we can do that now. Okay? So it could be n plus 1, n plus 1. Okay. Okay, so the only thing that we're going to do here is we're just going to multiply both sides by delta x. And so we get minus phi 4 n plus 1 plus phi 5 n plus 1 is equal to 2 delta x, which is 0.5. All right, and then that's it. And so traditionally, just because you are going to be solving this, typically you solve this in MATLAB, you would then take this set of equations and just put it in matrix form, just to make things a little bit easier to solve. Okay, so we're just going to extract the coefficients from these expressions here and put it into a matrix. Okay, and so we do that, we get following 5 by 5 matrix here. So first row is just going to be 1, 0, 0, 0, 0, and then minus 4.8, 10.6, minus 4.8, and then 0, 0. Okay. Next row is 0, minus 4.8, 10.6, minus 4.8, 0, and then 0, 0, minus 4.8, 10.6, minus 4.8. Okay. And then last row, we have 0, 0, 0, minus 1, 1. Okay. This is phi 1, n plus 1, phi 2, n plus 1, phi 3, n plus 1, phi 4, n plus 1, phi 5, n plus 1. I apologize, my writing got a little bit messy, so the phi terms don't exactly match up with the rows, but there's five rows and 5 phi terms. Okay. And then on the right-hand side, we have 1, and then phi 2 at n, phi 3 at n, phi 4 at n, and then 0.5. Okay. All right, and so this is about as far as you can take it, without a calculator, without MATLAB to help you. Okay. So let's go ahead and put a box around this. But if you did have access to MATLAB, right, you can go ahead and plug into this equation here. So the only thing that you have to plug in for is, of course, these guys right here on the right-hand side. Okay. Right, and so if you did have access to MATLAB, you just plug in the values for the solution at the current time step, okay? And if we're doing this on the first time step, we just have our initial conditions there. And so the initial conditions are just, 0, 0, 0, okay? And so for this one, I do have the result from one MATLAB evaluation. And so if we solve this linear system in MATLAB, we just plug in the matrix, we plug in that right-hand side vector, we do our backslash just like we did kind of in the first half of the class, we end up with the following. So B1 at 1, B2 at 1, B3 at 1, B4 time step 1, and then B5 at time step 1. Okay, so phi1 is just 1.0, phi2 is 0.8757, okay. phi3 is 0.9339, phi4 is 1.1867, and then phi5 is 1.6867. All right. Any questions on this result here? Okay. Okay, one final point before we head out for today, which I think kind of answers the most important question from the last 20 minutes, is why would we bother with implicit Euler, right? So implicit Euler is a lot more work, right? There's no kind of denying that. And so to invert a matrix or to solve a linear system, that's a lot more work, and it's a lot more work on the computer as well. Okay. So if implicit Euler and implicit methods in general are more work, then what's the point? Okay. Because if you work in computational, if you do CFD professionally, you do finite elements professionally, the name of the game is always going to be efficiency. So trying to get the best result possible for the least amount of effort, or maybe not effort, the least amount of computing power possible, right? And so implicit methods require more effort. There has to be a reason why, right? It can't just be, it just can't be just be for fun. The answer is stability. So implicit methods, you do have to put in a lot more computational effort to solve implicit problems. But the benefit or the prize that you get from this is that your simulation is much more likely to be stable. It's not going to diverge. It's not going to do kind of crazy stuff. So stability is an interesting thing. And so this is not the first time that we've come across this concept of stability, right? So if you think back to when we first introduced convection, right? We were introduced to a non-dimensional number called the Peclet number, right? And so the Peclet number, and by the way, I haven't forgotten, I am going to wear the Sanrio shirt someday. So I haven't forgotten. But the Peclet number told us that if that Peclet number was not satisfied for our convection problem, we'd end up with an unstable solution. So, our solution would just be, it would just diverge. Time stepping is similar. So in time stepping, you can also get an unstable solution, but it's due to the nature of the time stepping scheme. Okay. So explicit methods can be unstable if your time step size is not small enough. In fact, if you've had a chance to kind of play around with the most recent OpenFOAM activity, you'll have kind of experienced this, right? And so one part of the OpenFOAM activity is the Courant number, right? And so what the activity told you was that, if your Courant number was too high, in other words, if your Courant number is greater than 1, then you end up with an unstable solution. And if you ran a case where that happened, then you'll know that it's your simulation just kind of quits. It just solves for infinity and then it just quits. Okay. The Courant number is actually very straightforward. So the Courant number is basically just L delta T, or excuse me, U times delta T divided by delta X. Okay. Where delta T is the time step size, delta X is the grid size, and U is your velocity, right? And so for explicit schemes, you have a much more easier time to be unstable. Okay. We'll talk about this a bit more next time just because we are out of time. But just know that implicit methods you are going to be more stable, and that's why it requires more effort. Okay. All right. So thank you guys for coming today. I hope you guys have a good rest of your day, and we will finish up our discussion time marching on Wednesday. Remember, study guide is online. So study guide, if you look under week 13, it's there. And you should have everything you need today to do the first problem on the homework. Right? So the second problem 3 is a 2D problem. We'll go over that on Wednesday.
Which one?
David, I have 2 questions. Yep.
One, I sent you back the 500 sheet.
Yes, I got it. Yeah,
Okay.
I haven't had a chance yet just because it's been busy.
Sure.
Yeah.
Okay, and then the second question, do you know what the graph project's gonna look like?
Yeah.
You mean in terms of
For the specs?
yes, I'm working that one too. So basically I'm gonna have you do an extra component for the final project. So for the final project, what I'm thinking in this class, there'll be 2 options. We either do like a very complicated channel flow, kind of like a expanded activity, or you do an more complicated flow over an object. So that's gonna be the grad.
We do that plus something else.
Yeah.
Okay.
Yeah. So I'm not gonna make you do both. I think that's but I'm gonna have you do like extra post process on that.
Okay.
Yeah, that's one. Yeah.
Thank you.
For this one, quick question.
Yeah.
As we know that for the initial version is like 0.
Yep.
What does T-N?
So TN, okay, so we have to do that last too. So TN, that is the current time variable. So as you're time stepping, your time is updating as well, right? So let's go back to this example here. Right. So on the first time step size, T, or on the first time step, T is equal to 0, right? Because that's the initial. But then as you move forward, right, your time is actually updating by the time step size. So in this one, T is equal to 0.1 because we've gone forward 1 time, 1 step in time. So we've advanced by 1 time. And then by the second one here, T is equal to 0.2. We've gone up another. So for TN, let's plug in whatever.
The first thing so me and Derek are gonna yeah, first.
Okay.
So we're gonna be trying if there's anything we're gonna be missing from the 26th.
So you probably missed out on open from activity 3.
Unless we go on Zoom.
Yeah, so it would be on Zoom. So the last thing I need you for in person was you need to 2. So actually after that you can attend everything on Zoom.
That's the 22nd, I believe.
Yeah, 22nd. So I think it's before you guys leave. Yeah, so that would be probably.
Okay, for sure.
Yeah.
Okay, we'll probably just try to attend it on Zoom.
Yep.
I don't think there's any important exams.
No. Yeah, so midterm 2 will be the last in-person day, and after that, you guys can watch the YouTube lectures. It's all the same.
Okay,
Sounds good.
Yeah.
Thank you so much.
Yeah, no problem. Wait, what club you guys in there? You're competing.
It's a SAMPI. It's a Society for the Advancement of Material and Process Engineering.
It's the one where we're working with Dr. Wayne with it.
Oh, nice.
Yeah,
Oh, awesome.
it's
Awesome.
like composite materials. So we're making a carbon fiber I-beam.
Oh, that's awesome.
It's like an I-beam, but the goal is to like make it with composite materials
That's
as opposed to
probably-
like alloys usually.
Yeah.
So like the winner basically has the strongest beam but the lightest beam.
That's awesome.
Yeah.
Sick.
It's
That's
kind of,
cool.
it's kind of crazy.
Yeah,
'Cause,
but
like,
Yeah,
he was doing a lot of research and we found like strongest beam weighed, or the strongest beam weighed 300 grams and survived 7,000 pounds.
wow,
Yeah.
It's only 2 feet,
that's crazy.
know.
but like the process they made it with is like absurd. Like they had companies to help them out. and
Yeah,
stuff, too.
yeah. No, composites is wild. It's like,
Yeah.
it's crazy.
I know you teach FEA, right?
Yeah.
Yeah, that class would be helpful. Except I'm not taking that, so it's like everyone else uses FEA.
In the perfect world, I would have switched the classes, took FA first and then CFD later.
Oh.
It would close up
Definitely would
too
help.
fast. It
Yeah.
closed up way too
Yeah,
fast.
FEA is fun. Ironically, I didn't get to teach it this year.
Really?
Yeah, because I was gone last semester. I wasn't, I had a kid.
Yeah.
And this semester, I had to
So-
teach this one instead, so.
I think Funnet element
How to
is a
fix
little
all this
similar
right here,
to
right?
the scheme.
It is actually, yeah, very similar. Very,
Yeah,
very
that's what I was wondering.
Okay.
I was like,
Yeah.
maybe this will
Um,
help me understand FEA if I eventually take that.
Yeah, it's all related. All the computational technique courses,
Yeah.
they're
My
built on
thing is
similar
probably-
things.
Cool.
I gotta fix it.
All right.
Awesome, that's
Thank
cool.
So
Yeah,
cool. Thank you,
of course.
Yeah.
Thanks for, yeah. Okay.
See you guys Wednesday.
See you later.
You guys have questions?
Yeah, the first one.
Okay, let me close up the Zoom and.
Will there ever be cases where, cause I know I've